MIT is a bit like drinking from a fire hose, and I think that that's part of what we seek to experience when we spend time at MIT, when we sort of decide to build our careers here. If you were to ask me, if you were to tell me, okay, you can only talk to 3 people about the implications of AI for business and society, and you will only get to talk to these 3 people and no one else for the next 3, 4, or 5 years, I think these are the 3 people that I would pick to talk to. They have varied takes on it, varied experiences that really give them a well-rounded and absolutely deep understanding of what to think about and how to think about it. And I love that they all share with me privately that it's not clear that we know exactly what to think. We only know how to think about these problems at the current moment. So I want to introduce each one of them in turn and then get the panel started. The first one is Sendhil Mullainathan. He's a professor in the MIT Department of Economics and the MIT Electrical Engineering and Computer Science Department. One of the people that I love listening to most in talking about any type of research is Sendhil. He's a MacArthur Genius Award winner. It's not often that you have 2 MacArthur Genius Award winners and a John Bates Clark Medal winner on the same panel. So it's a huge treat for me today. UK Wired called him one of the 50 people who will change the world. He's done amazing research using economics and behavioral science and causal inference tools about poverty, about judicial decision-making, CEO pay, how competition affects media bias, and many other things. So Sendhil Mullainathan, please join us all the way at the end. Next up is Susan Athey. She's the Economics of Technology professor at Stanford Graduate School of Business. She's the recipient of the John Bates Clark Medal Award, awarded by the American Economics Association to the economist under 40 who has made the greatest contributions to thought and knowledge. She has been the chief economist for Microsoft for 6 years. She was also from 2022 to 2024 the chief economist at the U.S. Department of Justice in the Antitrust Division. And picking Susan's brain is one of the most enlightening things that one can do for 90 minutes. She's got amazing insight, very, very deep, and we're really, really honored to have her with us today, Susan Athey. And last but not least, Daniela Russ. She's the Andrew and Erna Viterbi Professor of Electrical Engineering and Computer Science and Director of the Computer Science and Artificial Intelligence Lab, CSAIL. She's also Deputy Dean of Research for the Schwarzman College of Computing at MIT. Daniela is also a MacArthur Genius Award winner. Her research addresses the promise of pervasive robotics and robots, increasing the ability of machines to reason, to learn, and adapt to complex tasks in human-centered environments, from transportation to manufacturing, agriculture, construction, monitoring the environment, underwater exploration, smart cities, medicine, in-home tasks such as cooking, and many other things. I don't know how she gets it done, but she put out 2 books this year on AI. It's pretty impressive. And listening to her think about the intersection of digital and physical robotics and how these worlds are blending together to shape our digital future is incredibly enlightening. Daniela Russ. Okay, so it's really my pleasure to sort of get the conversation going, but I also want to encourage you to start thinking about your questions because it's not often that you get to interact and ask people of this caliber the questions that are on your mind about this revolution. And I'm also I want to forewarn you that we talked before the panel that we're kind of not going to spare any punches. I've asked them to essentially really give us the fire hose experience and really go deep instead of sort of just stay at the surface level of this conversation. So I want to start with you, Sendhil. You've been thinking recently about how machine learning and generative models can aid in our ability to uncover new theories and new hypotheses about the world. I mean, we know that GenAI and machine learning can be useful for analyzing data and finding the answers to questions, but really you sort of flipped it on its head and said, can we use this new technology to help us understand how to ask good questions in a systematic and rigorous way? You've thought about how we can morph implicit theories into novel hypotheses, how to challenge formal theories with inputs that generate anomalies that then force the theories to evolve, which I think is very interesting. So can you please explain how supervised and generative models can help us generate new theories and hypotheses? Can you talk a little bit about the challenges of automating this process, especially the part about anomalies getting fed back into theories? And then also discuss whether similar machinery, which I haven't heard you talk about as much, could search the space of the novel hypotheses and tell us which areas of theory or hypothesis are most likely to produce the largest leaps in our understanding given what we know.
Great. I mean, that's not much to do, so we'll take care of that in a few sentences. Your introduction made me think that we're going to be stuck here for 4 or 5 years, so I'm just settling in a little bit. Let me just take a step back of a sort of a presumption behind the work that you're describing and the questions that we're asking. And I think to see that presumption most clearly, I think it's worth noting something that is actually in the air right now about a lot of AI. And what is, I think, missing in that? So let me summarize like a what-if question. What if we could invent algorithms that could do everything a human being can? Like, wouldn't that be amazing? And I think that perspective kind of permeates the water that we're in. And I think the fork in the road that we take is that really such an aspiration? That kind of puts a ceiling on what we can expect. It also means we're spending lots of cycles replicating what people can do. So what if we ask a different question? What are things algorithms can do uniquely that humans could never even dream of? So to do this, if I have time to tell a little story, I'll tell a story that'll seem it's just fun, but it's a fun story with a hint of a lesson. So the fun story, how many people here have watched The Wizard of Oz? Oh, that's good. How many have read The Wizard of Oz? Wow. Oh, fantastic. How many have read all 30 books? What? Amazing. Amazing. Oh, this is fantastic. So there's one Oz head here. So that's fantastic. I love that. That's never happened to me before. And the reason I'm asking this is that in The Wizard of Oz, there's actually a deep controversy that involves book 15. So Frank Baum died while writing book 15. Ruth Plumley Thompson took over and wrote the other 15 odd books. But book 15 is a source of a lot of controversy amongst the people who really study this topic. The controversy is who actually wrote it. So in fact, there are published versions that says, blah, 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 Frank Baum. Published versions that say Ruth Plumley Thompson. Published versions that say Frank Baum and Ruth Plumley Thompson. In the small group of people, and I do say small here, who have spent their lives answering this question, they have closely read the book, trying to figure out, and they debate, and you may not believe this, but academics put a lot of energy into tiny little things. And in that scenario, something kind of entered the foray that was kind of almost like a bomb that just effectively disrupted this field dramatically. It was a paper in a journal with, I think, the best title that I've ever heard of a journal title, Chance. I like that because it's like, shouldn't everything be published there? Isn't all of life chance? So what that paper did was it said, I'm going to train an algorithm. The algorithm is going to be given 5,000 word blocks and a label. This is a bound block. This is a Plumlee-Thompson block. And they only did it in the 1 to 14 books and the 16 to 30 books. Out of sample for those books, they found you can actually get an algorithm that gets to AUC of 1, like predicts perfectly, which is astonishing. Then they applied the algorithm to book 15. And it was like night and day. Until chapter 12, it's all Baum. Starting at chapter 15, it's all Ruth Plumlee-Thompson. It was the end of the discussion. So definitive. What made the algorithm astonishing is, one, how did this thing see something that all these humans in language, this activity that we understand, that we built, couldn't see? But there's two other astonishing things I should tell you about this. Astonishing thing two, the algorithm was not actually given the entire text. When it was given the 5,000 words, all the nouns, all the adjectives, all the verbs were deleted. So what's left? I didn't pay much attention in English class. I thought that was it. But it turns out there are things like to and the and it. These are called connector words. These words are actually the most common words in English, but we don't even notice them. And what you found was those words that are invisible to us, I call this a language exhaust, those words that are invisible to us are actually contain a ton of signal. The other astonishing thing about this, so not only did the algorithm see something we couldn't, it saw something we couldn't in something that we don't even quite process. The third astonishing story about this is I a little bit lied to you. I used the language of supervised learning and labels. This paper is from 2003. It is not industrial scale deep learning. It was principal components analysis. Why I'm saying that is because tasks that are extremely easy for algorithms can be extremely hard for us. And those are the places where there are huge gains. Second, those tasks which are not about what we know, that are not predict what a human would do here, get a label from a radiologist, do as well as a radiologist, but instead predicts things that are ground truth, outcomes that we don't know, the outcomes that we don't understand, and then try to understand what drives them. That's the beginning of this work. The beginning of this work is to ask that question.
Yeah, please.
Yeah, so that's such a great story. I love it, and I love the conclusion that it's humans and machines working together. I just wanted to give you a bit of color here in the context of a concrete application in medicine, so you can wrap your hands around what Sendhil spoke about so eloquently. So a couple of years ago, researchers at Harvard trained machine learning to identify lymph node cells and classify them as cancer or not cancer. And then they ran an experiment where they asked doctors and the AI system to solve this task. So at first they asked the doctors, and the doctors made 3.5% error. Then they asked the deep learning AI system, and the deep learning AI system made 7.5% error. Then they put the doctors and the AI system together, and the performance improved by 80%, 80%. That's because doctors saw some things, the AI machines saw something different. When you put it all together, the solution had the best of both worlds. And that's a good way to think about AI, to think about intelligent machines as tools that augment and complement us, that can assist us, that can augment us, in some cases that can automate tasks for us, as long as the decision-making remains with a human.
I love that example. And if I were to build more on that example, getting back to Sinan's, this is a perfect example. Let's just go forward there. Starting with that medical example, you can now ask, the two together did better. What is it the algorithm saw that humans didn't see? How would we go about extracting that information? Does that tell us anything about cancer that cancer researchers haven't understood? Could that feed back into science? I think that pathway where we move past this task at hand and ask, can we start increasing the understanding we have underneath the problem? to deepen that understanding and build upward is kind of the next step of augmenting for this task. But then what about the bigger task? The bigger task being we're exploiting some understanding to do something. Can we now build that shared understanding? So if I continue with the medical example, which is like a great example. Or Mo, do you want to?
Yeah, no, I just want to say something to follow up. Is that okay? Are we taking over?
Yeah.
Sorry.
It's fun. We're here to talk to each other.
I'm so excited about all the questions you're putting in front of us, and there is an even bigger opportunity, right? So if you think about these tools today, these tools are deployed in the most advanced cancer treatment centers around the world. But imagine a future where everyone had access to these tools, where an overworked doctor who does not have time to stay on top of the latest and greatest clinical trials can offer her patients the greatest treatments, the greatest opportunities that are most related to the condition of the human that they are trying to help. I think that there is just tremendous opportunity to kind of tap into this kind of global knowledge and support so many people.
So I want to sharpen this just a little bit, because I want to ask you a specific question and you, Daniela, a specific question, so that we can set up a question that I really want to ask Susan that sort of brings this all together. So what you're describing,
I think you're 3 moves ahead.
What you're describing with Wizard of Oz, but then also, in the case of the medical example, is an example or examples where machines can do things that humans can't do, and in fact, where machines can see things that humans can't see. And you've done work to understand machine analysis of data, providing us with new questions. For instance, in the criminal justice case, how are bail decisions being made and why? Analyzing it by thinking about it in the ivory tower with a notepad. And I wonder how judges think only gets us so far as human beings, but when you put a machine on it and you learn something from it, then you can say, okay, now I can see what the machine saw and ask questions that are now going to be productive. And before you answer, Daniela, the follow-up to you is, the machine is now going to evolve, and it's going to evolve from chatbot to agent, from language model to world model. What does that mean for what the machine is going to be able to see and do? So we'll start with Sendhil, then we'll go to Daniela, and then I'm going to ask Susan sort of the penultimate question there about what this all means.
Fabulous. Yeah, so let me take Daniela's example in medicine and the Wizard of Oz example and kind of concretize it into one very specific thing I want you all to go along for the ride for. But then I promise you it applies to many things. So picture you're a pretrial judge. What that means is someone's going to come in front of you. They have just been arrested. In a couple of minutes, 5 minutes, you're going to have to decide whether they should wait in jail or whether they should go home. You're not deciding their guilt. You're simply just deciding, do they pose a risk to society? You make this decision many times a day. But you don't know if you're making the decision well or badly. And I, as a behavioral scientist, would like to know what drives your decision. So I can come up with hypotheses, and people have done this. They've done things like, I wonder if mood matters. And there's actually quite an amazing study on this for judges, not pretrial, but judges in general, where if the local football team loses, judges are much harsher. And if the local football team wins, the college football team, this was in Louisiana, I'm not making any of this up, this is real, you're actually much more lenient. So we can test hypotheses like that. But somehow the rate limiting step is my ability to come up with these hypotheses. That's unfortunate. It's unfortunate given that we've got so much data on this judge. So what we did is we sort of turned the camera on the judge and said, let me predict what the judge will do. And let me throw everything into the pot. And it turns out when you do that, you can get a pretty good predictive model of the judge. And the fifth most important feature is whether the current charge, I think it's a drug crime. The fourth most is violent crime. You kind of walk up the ladder, and you get a bunch of current charges. But it turns out the number one most predictive feature for what the judge will do, and it's actually more predictive than every other thing in the data put together. It explains about half of the predictable variation. One thing is the mugshot. So the face of the person entirely predicts what the judge will do. Not half. I shouldn't overstate. To judges, this is a surprise. They didn't know this about themselves. If you dig a little deeper and you ask public defenders, what will it be? They're like, well, it's probably the race, probably gender. So you can look, and this is the morphing that's you can build tools to combine generative models like GANs with predictive models to try and morph and say, how would you change this mugshot to maximally change detention or release? You can start looking at those photos. Humans can look at them and say, what is the judge looking at? And features start to pop out. So it turns out one thing that really matters, it's ex post obvious, is well-groomed. Someone who's well-groomed is much more likely to be released. The part that's not obvious is how much more. It's about 50% of the effect of having committed a violent crime. The second feature is far less obvious. I did not anticipate this. It's full-faced. How fat-faced are you? This one is so not obvious, I think the sign is not obvious. How many people, by show of hands, think that if you're heavy-faced, you're more likely to be released? Raise your hand if you got a guess. No guesses. How many think you're more likely to be jailed? Yeah, at least some are willing to say more likely to be jailed. Yeah. The rest of you have no idea, like me. Or you need more coffee. The answer is heavy-faced people are much more likely to be released. And again, the magnitude is huge. It's about the same as like about half of a violent crime. So this is Sinan's point. But I also want to go back to Daniela's point about augmentation. One way we can augment is to agree on the task and do better. But the other way we can augment is to have the algorithm serve as a mirror of sorts. If you're a professional football player in the United States, in the NFL, you have an assistant coach who on Tuesday or Wednesday between games will sit with you and look over the tape and see every move you made, every snap, the footwork. Oh, you put your left foot here, maybe you should have done this. Now, I realize that a judge deciding on the future of people's lives is not as important as a football player. But where is the film review for the judge? Mm-hmm. Where is the film review for any expert? Daniela's point about doctors. Where does a doctor get to do film review? We don't, because there are no algorithms for that. There are no institutions for that. But something like this illustrates how we can probably close the whole cycle. I'm being a bit optimistic here. We have not closed the whole cycle, but it is showing you we have the raw ingredients to close the whole cycle and actually build augmentation tools that are not simply about doing better on this decision, super valuable, but also about improving people's understanding of their own decisions and thereby increasing how we do on all future decisions. So I'll stop there.
Yeah, so Daniela, as we think about the technology side, language models to agents, from language models to world models, from sort of chatbots to agents, what can we expect from our soon-to-be advisors and tape rollers in the expert domains?
So let me start by observing that the legal domain is very interesting, and it also highlights capabilities that we can have today. I was recently talking to a friend of mine who said, yeah, we use generative AI to summarize documents that otherwise would have taken a whole week for a human to read. And so we pull out the essential bits, and we can use that to fill out forms. We can use the summaries in much more effective ways. So there is already a lot of benefit, broad benefit, from the tools that we have today. But we have to remember that the tools that we have today operate extraordinarily well in the digital world using statistics. They do not understand anything about the physical world. They do not understand physics. They do not understand constraints. You cannot give them instructions. What you can do with statistics will be done really well by the tools that we have today. But if you have applications that involve the physical world with its physics laws and challenges, the tools that we have today are not enough. Now, if you think about world models, how we all navigate the world, we actually make representations about the world. We create our own mental ideas about who's going to do what, when you're going to clap, when you're going to laugh, etc. And so all of that guides us, guides how we behave, how we make decisions. We are interested in building AI agents that understand the physical world, that can create answers that are consistent with the physics laws of the physical world. And so a simple example that you might visualize is what happens if you want to use generative AI for manufacturing. Well, if you ask your favorite generative AI program, let's say ChatGPT, to create a new device for you, you will get a fantastical picture. And that's okay, because the fantastical picture doesn't have to do anything. But if you have to create something that works in the physical world, that's not enough. And so then the question is, how do we put this kind of extra knowledge that enables our machines to reason about the physical world? And this is not just for robots. This is not just for manufacturing. Anything that has a physical component, the power grid, medical decision-making, supporting people in education, anything that has a physical component requires that we reason about physics. And so we can explicitly put models of the world in our solutions, or we can connect our solutions to simulations. And I'll give you two concrete examples. In my research group, we've been thinking about a new way of building AI solutions. We call it liquid networks. We have a company that recently did a product launch called BIG.AI. And so the fundamental basis for liquid networks is physics-based. It's not statistical. In a typical neural network, the neuron computes a very simple function. It adds some numbers, puts them through some simple math like thresholding, and puts out a 0 or 1. And this is complicated because it's happening across millions of computational units. And for this reason, it's not really easy for us to predict what the system will do and how it will reach its decision. In a liquid network, the neural computation is a differential equation that is actually inspired by nature. And you might be surprised to hear that it's inspired by a humble worm that has inspired a lot of neuroscience literature. So there's a little worm called C. elegans. And the neural structure of C. elegans has been completely mapped. We understand the biochemistry of the neural computation. We understand what happens on synapses. And these are not 0-1 computations. These are analog computations. And so we took inspiration from the humble worm who lives happily on 302 neurons, in stark contrast with the billions of neurons in the human brain. And we created a new type of AI solution that is physics-based, where the physics of the world is kind of captured in the structure of the model. So that's one way to think about world representations. Another way is to connect your favorite statistics-based feed-forward memorizer, like ChatGPT, like any transformers that are out there, to connect that to a simulation engine, and to use the signal from the simulation engine back into the model, and to continuously train until the simulation says that your result is the right one. So for any type of physics-based application or physical application, you have to capture the constraints. You have to capture the rules of the world. And these are two ways in which you could do it.
So Susan, I want to ask you, we're talking at a higher level about machines building hypotheses and theories, machines representing and reasoning about the world. and machines sort of thinking about the consequences of their actions. In the physical world, as you were talking, I was thinking to myself, there's no reason why I can't think about the physical reasoning and representation of a machine and take the physical out and input tax policy and have the same approach to the problem. So in all of these top-level domains of problem, I want to dial down into one specific element that is relevant and absolutely critical to all of them, which is causal reasoning. Okay, so causal modeling has long been a focus in the empirical social sciences, and in recent years, you've been thinking about how to marry predictive machine learning and causal methods to estimate causal effects. Although causality seems to be gaining more attention in the machine learning community, the generative models and the LLMs of most big tech companies are basically going all in on a prediction approach to problem solving rather than a causal reasoning approach. And this seems absolutely critical to everything we've talked about so far if we intend to intervene in the world and make some policy or the machine does something. So to set the stage, can you tell us a little bit about the difference between prediction and causal modeling and why it matters? What are some examples of modern AI that take a causal perspective? Do you agree that LLMs are purely predictive, or what does it mean for an LLM to be causal, or could it be causal? And how does your understanding of causality affect the advice you would give for people building and using LLMs in business applications and societal applications in general?
Yeah, so lots of questions. Let me start from how I came to this problem. So in 2007, I was then teaching at Harvard. I was kind of pulled out of my office and very quickly landed in a high-level position at Microsoft. And one of the big things I worked on there was the search engine. I worked on policy around the search engine, but also the operation of it. And I was befuddled by multiple things. So it was being run by lots and lots of machine learning engineers. And the way that you're producing search results is that you're taking a query that comes in and you're classifying it into different groups and then trying to match it up and ultimately predict what people will click on. On the advertising side, there's a marketplace with advertisers, and the advertisers are placing bids to be shown next to the search results. So there were a lot of things that seemed like mistakes happening, and I was trying to understand how are these mistakes happening? Because things don't just randomly happen. Like where are the gaps? You have all these brilliant scientists, brilliant engineers building stuff, and they're making systematic mistakes. Where is that coming from? And I think a lot of the issue was that people had thought about the whole machine as a predictive machine and a predictive algorithm, but they weren't necessarily thinking about the decisions that were being made on top of it. So just to give an example, if you change something on the user experience, that will change what ads are shown in some way. They might be more prominent, or you might get different ads if you change your ranking algorithms. That, in the short run, you can measure how users click. And so they were running lots of randomized experiments to try to learn cause and effect of changing how they ranked things. But they weren't factoring in the fact that afterwards, advertisers would look at their experience, they would look at their clicks, they would look at the click quality, they would look at how much they would sell, and decide how to change their bids, or whether they even wanted to keep bidding on this system. And so without a theory, a conceptual theory of the fact that you are actually intervening on a marketplace where people respond, you could make systematic mistakes. And without giving all the details, that would lead to often lower quality ads because you weren't factoring in the fact that if you gave advertisers lots of bad clicks, ultimately they wouldn't pay as much for them. So this got me sort of started thinking about, what are the amazing superpowers of predictive machine learning, and I brought a lot of that into economics, but also what are the huge blind spots and in the end, the way that black box models can be easily operationalized, and the way that systems can be broken into small components and have another big thing about the search engine is it was broken into lots and lots of teams, small teams, like 8 people, 10 people, building stuff. And how can you run something so complicated with independent teams? Well, each of them was given an objective, that's something that you could measure in the data, and then they were training models to achieve that objective, and you'd hold out a test set and say, okay, I can classify, is this a Wikipedia query, or is this a celebrity query, or is this a weather query? And then you had the ground truth, and you could just check whether that was right. So that paradigm has huge advantages. So any problem you can decompose into lots of predictive problems is something that you can decentralize. You can decentralize it organizationally to teams, and you can give it to a black box AI or machine learning algorithm and not really care how or why it works. And you can replace out one algorithm with another algorithm. All you have to do is just make sure that this algorithm is doing the thing that you wanted it to do. And that works well for components of problems. But it doesn't solve everything. So when I would argue with the machine learners, they would tell me, no, we do understand everything. You know, I don't know, what do economists know about any of this? You know, go home. So I tried to come up with examples to explain what they were missing. So here's one of the examples simple example. So imagine that you are a business person who needs to know how many people are staying at the hotel across the street. Maybe you're a competing hotel, maybe you're a restaurant on the street, but you have this prediction task. You want to know how many people are in that hotel, but you don't have access to their quantity bookings. So you get this great idea. I'm going to create a supervised machine learning data set. I'm going to sit someone outside the hotel for a month and write down how many people come and go, so I'll get some data on the quantity. That's the thing I'm trying to predict. And then I'll scrape prices off of hotels.com, and I'll build a predictive model. So you could do this at larger scale, of course. So what you're trying to predict is quantity, which you can't see directly. But what you will be able to see directly are prices, because you can always just scrape those off the web. So you ask your junior engineer to go build a model. Now here's a question, another survey. So if you build the predictive model, it fits great, say it predicts, you know, with high accuracy. If you change an input feature, which is the price, and you increase the price, you see a higher price today on hotels.com for that hotel. Does that mean that the quantity is higher than average or lower than average? So higher price, who thinks that should lead to a lower than average quantity? That's the intuitive thing. Higher prices, people buy less. But that would be wrong. That's absolutely opposite. So why are the prices high? Those of you who are business travelers know, if you ever go to a conference and you forget to book your hotel till the last minute, the prices are very high. Any of you who want to take your kids on school vacation and you wait till the last minute and you try to book, the prices are high. That's because, how are the prices determined? The prices are determined using a yield management software, which raises the price when their hotel is almost full. And of course, often same for airplane tickets and other things. So in the data, if you wanted to predict whether the hotel across the street is full, a very high price probably means the hotel is full. That would be a great predictive model. So you shouldn't fire your junior engineer for showing that high prices predict high quantity. But now, suppose somebody says, oh, wow, we've got machine learning in our organization now. Now we've got all this data about prices and quantities. So let's use it to set hotel prices. So if you take this predictive model and try to ask it a causal question, what happens if I increase my price? Well, certainly not, you'll sell more, okay? You won't sell more by raising your price, just because in the past, there was a correlation between high prices and high quantities. That is, that high prices were predictive on average of high quantity. It doesn't mean that if you change the price, you will change the quantity. And that's the difference between a causal model and a predictive model. Okay, so if you think of what ChatGPT and these other things are doing, is they're doing prediction. So they're saying, like, on average, if you write these words, what's more likely to be the next word? And that's very helpful. For many purposes, that's exactly what you want. But it may not be what you want if you want to change something. And so formally, mathematically, you have to be very careful with how you write these things down. You can't just write down probability distributions. You have to talk about changing probability distributions. And if you change your price, that would be moving the price away from its correlation with everything else in the environment that would normally be there. So, okay, so then because economists noticed this thing a long, long time ago because we tried to estimate demand curves. We tried to estimate what happens when you change price, and most data sets you look at have a positive correlation between price and quantity. Because most of the time, prices are changing because of some underlying thing, like demand shocks. Okay, so it's a very common thing. Like, people write their entire PhD thesis and spend like 3 years just trying to get their demand curve to slope down, that higher prices lead to less quantity. And it's hard to do. Why is it hard to do? Because there's often not enough natural experiments or real experiments in the data where somebody actually changed the price for the purpose of exploration. And if you have to have done that for the right reason, and the analyst has to know the difference between times that prices changed because there was a demand shock or something else, and the times that prices changed for another reason, because they were running an experiment, or in this case, a cost shock would be a natural thing that would help you understand how consumers respond. So in general, there's theorems as well as decades of empirical practice showing that this is actually very hard to do. And it's hard to do it well. And so often, if you want to answer these questions, you actually have to be inside a firm running experiments, or at least having very clear understanding of why prices changed in the past before you could use it to make decisions. Okay, so that's a very hard thing. So I can say, he asked me like a 4-part question. But so in the physical world, this is actually easier in a way than in an economic world. Because, so there's an area, so this is like the supervised machine learning world. There's an area, a subpart of AI called reinforcement learning, or bandits, which I also have worked in, that tries to have agents that are themselves running experiments. So instead of the AI just like passively answering a question for you or making a prediction, it's the algorithm itself is testing. And then in principle, the algorithm is designing the experiments. It knows that it ran the experiment, and it can incorporate the data as a causal statistician. So it turns out that the first round of these algorithms also were not very good causal statisticians, but that has been improving, and that's something that I've been working on. They have to really, it's very subtle to use data that was collected when you were trying to optimize something. Like if I'm thinking about customers coming in and I set higher prices for some customers and lower prices for other customers, then I need to really factor in the fact that I did that in the past when I draw my conclusions. And that requires a lot of sophisticated statistics. And it's hard. Another lesson out of all this is like when you're trying to do this in large tech firms, even and I've been on the boards of many tech firms, large tech firms, small tech firms, done a lot of these projects. Even the very, very largest firms we have, they're running thousands of experiments a year. They can be very good at prediction, but testing the effect of changing something is always noisy, much noisier. And part of it is because they're already doing pretty good things, so that the improvements they make are often are small. But trying to learn about cause and effect is usually like an order of magnitude, 100, 1,000, 10,000 times harder than learning about just predicting what people do. It's very easy to say this kind of people click a lot, these people don't click a lot. It's very hard to learn what makes them click more. Like if you think about the last election, you can sort of predict who's going to click on a political ad, but like how do you figure out what's going to change somebody's mind? What's going to make them vote differently? You have to test, you might test 1,000 pieces of advertising copy, but you need to get a lot of people to start learning what's actually changing their mind. And sometimes minds are hard to change. So this is a really big discrepancy. So now if I pull this all back to like these language models and what they're doing, right now they're just predictive. And a first reaction is just like, you should be very skeptical about using something that was trained as a predictive model as a decision model. Like, to a first approximation, you shouldn't do it. Like, you should, if it's trained to predict, you should use it to predict. And if you want to make decisions, you need to put a human on top of it, who understands the input. You need to run experiments on top of it. You need to do something else on top of it to make it useful at all. Okay, but now let me give a counterpoint. And actually, this is where I would love to get Danielle to react to this, but let me tell the story first. Is like, okay, the physical world is actually in some ways easier. Like the economic world is very complicated. There are incentives, there are equilibria, there might be things you've never seen people do before. But imagine that I just am watching like molecules bounce around, or say I put balls in a pool table and I randomly like drop additional balls on them or shock them. And I just take a very, very long video of that. And then I try to build a model to predict where the balls go next. If most of what's shocking the system are just balls randomly dropping in or maybe getting pulled out of the system, I'm actually implicitly doing a lot of experiments. And if most of the variation that's happening is either following a set of physical laws or is like random perturbations, if I get very good at predicting where the next ball goes, I probably have built a good model of physics, or at least the kind of physics that's necessary for balls bouncing around. And if I have every possible way to bounce balls in, and I have zillions of hours of video, and I can predict the next frame, then actually I probably could use that to understand, like, should I drop a ball here or drop a ball there? Because I want to predict what happens if I drop a ball here, versus what happens if I drop a ball there. If I have a good prediction of both, and I care where the balls go, I can use those predictions and actually make a decision based on them. So it's not that a really, really good predictive model can't be used for decisions. It's that a lot of it's about the data. Did the data you collected have the same kinds of experiments that are similar to the decision you're making? And I'll give one more, let me bring this back to a business context. So one business context you could use would be forecasting. So I want to forecast, and I'm an operational manager, and I'm trying to figure out, how much inventory I need. And I have all my data from the past, and I say, okay, if I sell this much, if this is what's happening in January, February, March, how does that predict what I'm going to sell in April? Okay? So that kind of predictive model potentially could be used for decisions. If the world is marching along in the same way it's always marched along, then you can take January, February, March, you can predict April, and make some decisions on it about inventory. But now what if I tell you that also sometimes you're not going to make your quarterly numbers, and somebody looks at that forecast, some business person looks at that forecast and says, we're looking low. We better sell more this quarter. Tell your salespeople to try to accelerate some sales. Pull some sales in from April to March. That never happens, right? Okay, so you provide an incentive, you just tell them you're going to give the salespeople extra bonuses, you let them do some discounting to make sure that you sell a lot in March, and that way your quarterly numbers look good. Okay, now if you use that same model to predict April, your model's not going to do very well, because in fact, usually when things are going high in March, that's because demand is increasing and you're on an upward trend and you're going to sell more in April. But if you're sold a lot in March because you pulled sales forward from April to March with incentives, then actually April's going to look really bad. So you better not, use if you have decisions like that happening in the background, or you're using this type of model to make those kinds of decisions. Now the difference between prediction and causality becomes fundamental, and you actually can't trust your machine anymore. And then you would need to understand not just the regular prediction, but also like what other kinds of decisions do people make in reaction to your predictions. And if you have a better prediction engine, it might actually change their reactions. So this gets to be a very complicated world. So just dropping predictive AI into a company and hoping good things will happen could be perverse, in fact. So that's kind of my take on where we are, and I would say that both the science and the implementation of this are really like kind of nowhere for the And they were literally nowhere in the big tech companies when I was there in the late aughts and early 2010s. It's not that nobody's thinking about this, and people from robotics in certain places have already been thinking about this for a long time. It's the combination that's really the frontier.
Daniela, do you want to react to that, and then I'll go to Sendhil?
Yes, that was so interesting, Susan. So I have a couple of observations. Let me start with the last question you posed. How is this idea of watching balls bounce relating to world models? And I want to go back to your business idea or to your business example, where you say, yeah, you can predict inventory, but then there is an additional action that was not part of your data, and that changes things. And so it's kind of the same in the physical world. We have observables and non-observables. So in your business example, the inventory is observable, but this additional action is not observable. In the physical world, you have the same. So you can watch the balls bouncing, but now suppose you have a human entering the scene on a horse. The system is not going to be able to differentiate between the human and the horse. The system will think that's a single creature, and that will have consequences to what you can actually learn. So in the physical world, you might be able to learn kinematics, but you will not be able to learn the dynamics of the task unless you actually have data about the task. And so I don't really believe that we can teach machines how to execute tasks by watching videos. Some of my colleagues have models with a lot of videos of how humans work in the kitchen or how humans fold laundry. But what's missing from those videos is the forces and torques that we apply when we handle the knife that are part of dynamics, not the kinematics of the task. And so, yes, you can learn some things, but what you can learn is based on observables. You can learn kinematics, but even with kinematics, there are situations like the horseback rider where you're not going to learn that correctly. So we have to be very careful. And this actually takes me to my final point here, which is that most of the machine learning models that we have today are not causal. Transformers are not causal. Many of the neural ODE models are not causal. But there is a handful of causal models that are beginning to arrive. So these models are called state space models. Liquid networks are provably causal. There's a new type of model called linear oscillators. This one is inspired by the oscillations, the harmonic oscillations in the brain. So these are provably causal. The other models will learn the context of the task rather than the task. So if learning the task is important, please use a provably causal model. If learning the context of the task is important, you can use one of the other predictive models.
No, can I just bring that like across the finish line just to come back? When you sit in these conferences like this, you might have, instead of us, you might have had a bunch of people up there with hockey stick graphs. And I've sat in approximately like 1,000 of these things where there's, and I, for like the last 20 years of like hockey stick graphs about like how the AI is going to do everything and it's all perfect. And of course, when we all woke up one morning and started using ChatGPT, we all, even me, who understands why these claims are not possible or not plausible, using at least the current technology, I used to like, wow, this is really good. Maybe I underestimated. But ultimately, there is a ceiling from what you can do. And I think to state what Daniel said another way, it's that you have to have the right data. Like to learn, you have to have had the ability to see the experiment. Now, one reason you question is say, well, maybe it can just reason, maybe it can guess, maybe it can read all the scientific literature and make good guesses. So I'm not saying like there's these kind of insights and stuff may not pop out, but so that's a different pathway. Like it's forming hypotheses and theorizing and so on. But ultimately, the just prediction gets you a lot farther than I ever thought it would. I started as thinking it would get you like this far, and it's gotten us like this far, but ultimately it's not, it's about, if you don't have the right kind of data and usually combine it with some kind of modeling that tells you how to use the data, it's gonna be hard to get across the finish line. So people are, so it's amazing that people are building these things, but this is still like a tiny share of what's happening commercially. It's still like on the frontier. But that's, I think, where it's going to have to go if you want it to be more generally smart.
So I just want to make sure that we get to a couple of questions and leave enough time for the audience. And in the spirit of what do managers do with this, in the spirit of experts with an AI sort of giving them tape to study themselves in a sense, and in the spirit of sort of real business applications, I want to turn to you, Sendhil, and ask you a question, but I want to tell a brief story which makes me think about how AI could assist me in some of the work that I do, which is that we were working with Airbnb to try to understand how it might affect their business if they changed their prices. So we thought to ourselves, and they thought to themselves, like any good manager and business leader would today, we should run an experiment. We should take a local geography. We should divide homes, into randomized control and treatment groups, and we should change the price of the treatment group homes and see what the effect on demand would be in that situation. And of course, the problem with that is that when you put some of the homes in the treatment group and some of the homes in the control group, and you change the prices of the treatment group homes, then suddenly you're changing demand for the control group homes, which then feeds back into the demand for the treatment group homes in a lot of ways. And so there's this interference between the control and treatment groups. And of course, as good experimenters, we thought to ourselves, well, how could we model that interference? How would the treatment group affect the control group? How would that effect spill over into the control group? But our brains are too puny to understand the vast, complex spillover effects that could be happening in that situation. But I'm thinking to myself that a machine with some data might be able to tell me more. And so my question to you, Sendhil, is, there's a ton of uncertainty right now. So what should managers be doing? How should their approach to this be given the uncertainty? Should they be substituting labor for machines? Should they be experimenting? How should they be thinking about it?
So let me build on what Susan and Daniela have said and kind of repackage it into an implication that is very direct from what they've said, but might not be obvious to the audience. And what I want to kind of argue is this is probably the biggest mistake every business person is making. And so to make the mistake very clear, let me contrast it with probably what is the typical sales pitch that you will be getting from an AI company. So the typical sales pitch is going to be something like, you do all these decisions, your company does all this stuff, look how much of it AI could help with. And you have all this data, look how much AI could help with that. This is a very sensible pitch. There are some caveats that are described. Now let me restate what Susan and Daniela said, which is that the data you have is actually not enough. You are missing several pieces of data. You are missing data about counterfactuals, things you could have tried that you didn't try, that you're missing unobservables, things that are not about that context. So actually, weirdly, you're in a data poor environment. And if you play that forward, what companies have been very successful with AI? It's been tech companies. And then you're like, well, obviously they're close to the tech, that's why they're successful. That's actually not it. It's because a lot of them are about digital platforms. And so their entire business starts by being instrumented, and a ton of data is already collected. Their consumer experiences are already in a data collected format. So Gap.com as a website is collecting a ton about what their consumers are doing, Gap, the company with physical real estate, is not collecting this data. It can't. So what I would argue the first thing people should do is they should actually be investing and thinking hard about how do we radically expand our data infrastructure, exactly along the lines that Susan and Daniela are indicating. How do we expand the infrastructure to make it easier to experiment? How do I expand the infrastructure to make it easier to start collecting new kinds of data that I'm not collecting? So a different way of saying this is the person who comes to you and says, oh, we can do so much with the data you have. From an economics point of view, what are they really saying? They're saying the returns to data have gone up. Let's just accept that. But if the returns to something has gone up, basic economics tells you what you should do. Get more of it. So actually, the value of data collection is at the highest point right now, I think, for all the reasons that have been said, but also just from the basics of it. Whereas I think the market tries to push you in a different direction, exploit what you have. And I would say that the biggest thing that we should be doing right now, if I were running a business, it would be to invest in data collection.
Amazing. And I want to ask one last question, and then I want you guys to get ready with your questions. So be thinking about that. And this question is to Susan. Susan, I'm going to tie one hand behind your back and give you a little bit of a time constraint. So you were the consulting chief economist at the Justice Department Antitrust Division.
Just chief economist.
Chief economist, okay. So in thinking outside of one firm, in thinking about the ecosystem of the whole marketplace, in thinking about how the technology is being developed, my question to you is, are you happy, satisfied, pleased with the current market structure of technology development? Is this going to enable rapid innovation and an equitable distribution of this technology in the hands of many to produce the greatest increases in welfare? And if you were sort of the omnipotent regulator, what would you do to make this better for all of us?
Great. Well, yeah. No, so I left government over the summer, and it was actually an amazing experience. And I do want to just mention how the people that we have working in government, especially high-skilled professionals, are really a national treasure who have given up 10x income outside in order to be very mission-driven. And so working with those people was really the best experience of my life in terms of a community of people to work with. So, this is like a multi-day discussion. When I was at DOJ, I ran a conference together with Stanford about competition in the AI industry. The videos are online if anybody wants to see them. It was also pretty in-depth. I can just try to give like a little bit of a bird's eye view of what people said at that conference and some of the takeaways I have about the industry. First of all, we broke the stack apart, and there are some, I think, relatively conceptually straightforward but tactically hard to solve problems about competition at the chips level. I'm going to leave that aside for today in interest of time. If you think about what it takes, if you want to think about the industry, what are the non-obvious things? I think people start talking about AI and they think about ChatGPT and they think about cloud as like parts of the stack, and of course the chips. But if you double click on the applications layer, I think thinking that through more makes it easier to predict where competition concerns will arise and what the industry structure is likely to be. So I think one of the things that's confusing is that ChatGPT is both like a developer tool. It's something that other developers can build on. It's like a science project itself, and it's directly a consumer product. And that's weird, where a consumer is basically interacting with it through the same API that a developer is. So it's hard to even talk about ChatGPT as one thing. So as a consumer product, right now we're interacting with it, but it's already starting to be a little bit of a platform and a marketplace where you can plug in other apps and use them together or separately. So there's a consumer product now, but that could turn into like an app store kind of thing that goes directly to a consumer. But that could end up competing with something that might sit on a device and be like your global assistant. And one of the reasons the devices matter is that we've seen that if there's a device that's locked down by an operating system, and which in turn has an app store that's also locked down, then the firm that's doing all of that locking down has a lot of control. And so that firm, if you want to have an app that's going to open up lots of other different apps on your phone and have access, sort of operating system level access to things, that is going to be at the pleasure of the locked down operating system. And so that's going to tell us something about which firms might win or have products or control those products. So if it's mobile, then we know right now who those firms are. Maybe in the end you'll get another mobile firm coming out of all of this because somebody wants to provide you such an assistant and they can't provide that assistant through the existing firms, but it's pretty hard to enter in mobile operating systems. So that's one thing as we think about the future. Do we think there's going to be these kind of omnipresent agents that live on a device that's locked down? On the other hand, consumers might have lots of different apps, and they might also do certain tasks more on a computer that's a PC or something that's not locked down. And then that type of environment, there's more possibilities of who could be bringing you those services and in what way. So that's just on the consumer side. And then building on what Sendhil said earlier, what the tech firms have is not historical data. What the tech firms have is the ability to run experiments on their users and the fact that they have recorded their experiments in the past and learned from their experiments. Because that's the kind of data that you can use to make decisions and improve products. So any firm that's interacting with a lot of consumers may get better. Now, what's very interesting is today, those models are mostly, the big language models are trained on historical data. They're not really incorporating the user data a lot. But if, my prediction would be this will become true, I don't know this though, if what happens is that the user data gets integrated more and more and another layer on top of it, so you're no longer talking directly to ChatGPT, but you're talking to a layer in between that's improved with user data, then anybody who has a lot of user data will have an advantage at building those models. And whatever it is that has given them an advantage in collecting that user data, whether it's network effects in a social network, whether it's their big e-commerce presence, whether it's their search engine presence, whatever that is, will potentially still be an advantage at that next layer. So that might make you worry about at least concentrated oligopoly in these things, like maybe more than one, but not very many of these firms, because not very many firms are going to be able to attract enough consumers and do that. But it might be more than one, because there are social networks and there are search engines. It's not just one product that would allow you to have a lot of user interaction data. But the thing I think people are not thinking enough about is that a lot of this stuff is also happening on the B2B side. And the economics of B2B and the concentration in B2B are very different, because in B2B, like the business applications, you're not just locked down to a device. You're not just, dependent on whatever somebody will let go into an app store, but rather you're in a secure environment and you can create your own applications, and you're often running on devices other than locked down physical devices. In those worlds, we're going to have, there might be like SaaS, like a direct, somebody's just providing you, say, HR in a box, an AI HR in a box. You might have platform-sponsored SaaS, like Salesforce selling apps to Salesforce users. You might have businesses developing their own custom apps internally. And you might have developer tools that make it really easy in a low, no-code way for businesses to build their own internal apps. But in all of those use cases, I would expect that for the most part, the data, there's going to be a bifurcation of, like, there's some foundational stuff that helps you understand language and helps you understand the world, but then the business's the business's data is going to be combined with that, but crucially not shared across business customers, because business customers won't want that data shared. So that changes the scale economies, it changes the concentration. Also, businesses want each application to work really well. They're not going to just take like something which is good enough across everything. Like the HR thing has to really work, and the finance thing has to really work, and the inventory thing has to really work, which often leads to multiple providers of applications. So in that world, where there's some kind of foundational layer, but then a lot of value added and customization with local data, the industry structure might be less concentrated, potentially. But one key factor that affects all of this is the availability of open models. Because, and what we're finding, what I see today is that, and this is also true in my own research, is that fine-tuning open models with custom data can get you as good or better performance than the state-of-the-art largest language models. and that the smaller models are easier to customize and do stuff with, and they're cheaper for inference, they're cheaper to analyze. So in fact, like they're just better. That's what firms are choosing to do, even if they could afford to spend money on more expensive stuff. So then a big takeaway out of all of this then is two things. One is, think about the B2B when you think about concentration, because that is going to put limits on concentration. Think about there being lots of different use cases, but open models that make it really cheap for everyone to experiment and develop and give people control to develop internal applications and so on is going to be crucial. And if those get shut down because everybody's afraid of them, or just people, for some reason, a company stopped making them, or they're not good enough, then that could really increase the price of everything and decrease innovation.
So I'd love to hear questions from the audience. Why don't we start right here? Okay, great. Let's start over here, and then let's get a mic over here. Thank you, Carrie.
Tamsin Webster. I'm curious, to what extent are we exploring or potentially overlooking the opportunity that's created by gaps between machine learning, our prioritization of system 2 rational thinking, and what it is that we humans can do that AI cannot. And here's what I mean by that. I mean, I think that we can think back to like classic elephant and rider, and it seems like what we've been doing with AI has been trying to make a better rider. And yet the way that we make decisions is so deeply powered by system 1, fast thinking, and I think the more that we understand that this is not some big dumb animal driving a lot of our thinking and decision making. It's more like alien-powered octopi, right? Like potentially equally sentient. But it seems to me, I mean, Sendhil, you had brought up this point about we need to expand the data infrastructure. And I'm curious, isn't that us? Aren't we the data infrastructure of this kind of thinking that, from what I'm hearing, AI isn't even remotely close to being able to establish, from causal relationships to deep history to observation to other forms of knowing, other forms of knowledge, so that we haven't really, it seems, incorporated human learning into machine learning. And that seems like a hugely undiscovered country.
Well, human learning itself is a huge undiscovered country. So it's, but your point is actually very interesting, because transformers are the king of the planet right now. So most applications are transformer based, and the transformers are feed-forward networks that operate by memorizing and scaling. In fact, if you read the transformer paper, the third sentence says, we do away with convolution and with feedback, with recurrences. And so that's an interesting observation for me, because feedback and recurrences are salient, are very important to how we learn, and to how we reason about the world. And so what I get from that is that indeed, there is a ceiling to transformers, and thinking about other computational processes, for example, feedback mechanisms, it will be very important to increasing the capabilities of our AI systems. But that's not to say that the AI systems cannot do great things for us. We just need to we just need to be very careful at how we match the task that we want to solve and what AI can do for us for that task. And we need to be very clear about the value proposition in using AI. With AI, we can get speed, we can get knowledge, we can get insight, we can get creativity, we can get foresight, we can get mastery, we can even get empathy. There are so many different directions that AI can contribute. But just because a problem is solvable by AI, it doesn't mean that it makes economic sense to deploy AI to solve that problem. And so, for example, if you, my colleague Neil Thompson has a very interesting example in one of his recent works. So he talks about inspection. So inspection is something that can be done really well with AI because computer vision has advanced tremendously, and the inspection tasks are easy to do with machines. So now, suppose you're a baker and you want to use machine learning to inspect your dough once it's mixed. So a human can look at the dough for about 10 seconds and say, yeah, it's done or it's not done. But if you were to use a machine learning solution, which could do the same problem very well, you need the data, you need the AI expert, you need the cloud computing, you need the time to get it all together. So does it make economic sense? Probably not. However, maybe you make a platform and a lot of people use it, and then it might make economic sense.
Mm-hmm. Why don't we, did I see a hand over here? Yes, go ahead.
Hi, guys. Thanks so much. Rich Steele. This has been great. And your comments about the importance of data, right? How do we make decisions, and what should leaders be focusing on, right? More data, better data. When we think about the conflict between the need for speed and your AI companies who need to release their next version and their next version that has more capabilities, better outputs, and starting to hear now that, well, part of our challenge is we're running out of new data to make the models better, so we're going to start curating data and injecting, AI-provided data into the training models because that'll help us go faster. I thought we had some concerns about that, model collapse and AI data organically bleeding in. Now we're starting to hear, well, we're going to intentionally put some data in, but it's okay because we're being careful about it. We're picking and choosing what we put in. Who gets to decide what data we put in? Because aren't we deciding the answers before we've even asked the questions?
That is actually a very big question that implicates everything from bias in the outcomes to whether or not this will improve or make the models worse. Does anyone want to?
Sure, I would just say, I think, again, I have only small experience myself in my research building these things because of the compute limitations and so on. But I would say that my strong intuition, based on both science and experimentation and talking to many people who are out there doing things, is that the big thing is you need to match as Danielle said, match the AI to the problem and use it in the correct way. If that's the real differentiator, then you're more likely to put more emphasis on the second stage of this, where you're using your own data and you understand the data that's coming in and you're adapting it, or somebody as a service is adapting it across many organizations solving the same problem to the task. So I guess then I think you should be thinking about the data, like if you're making decisions about inventory management or supply chain management or hiring and firing or other types of things, those are like important decisions to you, then it will be important that you have a system that is tuned and on your data for your task, that understands what the key variables are that might have changed the distribution of your past performance, and that also allows you to collect outcomes and improve it and so on. So that system is really built on top of a foundation model. And then I think the foundation models are just making it much faster to understand basic patterns that go into that. So, by the way, I worked on text, many years ago, and I worked on it in the search engine. It used to be just really bad, and part of the problem is you needed like a lot of data, like more than a search engine scale data, to understand human language using the old models. Now we've figured out how to get a better understanding of text, and then with much smaller data sets, in downstream tasks, you get performance, you get things to work that didn't work before. So it's not to say that the foundation model isn't very important. It's just that I think of it as a two-step process. It's giving us like the basic understanding, and then there's a second step where you tailor it to your problem. And so in that world, you won't worry as much about what data is going into the foundation model because you're not really relying on it at that level of granularity. And also, like then from a data market content provider perspective, they might come in at this second stage as well. Like a content provider who makes high quality or specialized data might find that people are willing to pay for it in this second step where they really see the value because they need it to solve their problem. But this is a huge industry structure question. Like, if that's the way the technology is going to work, there's going to be an industry in the value added layer of data, of software, of tools, of services, software as a service, plugins, all this stuff. And that ecosystem is where all the most of the value added will be. And as long as the initial foundation layer stays relatively cheap due to, say, competition from open models, the prices stay low, then this whole industry will flow. But if it all gets pushed into this main layer, then a lot of those questions become much more important. Then there's a black box, and you just have to trust it, and you can't control it, and you don't know what goes into it, and you worry much more about all those things.
Yeah, so there's a lot of questions and to managers about how to build up more data and how to either share or keep data inside the organization in order to appropriate value, in order to affect whether or not the models are uniquely giving insights to the business or are now part of some more general situation. Yeah.
Yeah, I have to give the technologist perspective on this because it's true that we have these extraordinary tools. They give us extraordinary opportunities, but they're also flawed in many ways. They need too much data, they have bias, you might not, they're not robust, you don't understand what happens inside the black box. But as technologists, we understand that these are issues with the tools, and we actually set out to solve the issues, to develop technical solutions that could then be taken on by companies to be services for businesses. So here's one example. You can actually take a machine learning model and determine mathematically whether it's going to produce a biased result or not. And you can do so by analyzing the data used to train the model by deciding whether some features that you care about are overrepresented or underrepresented, and then you can resample to rebalance the data. You can do this to figure out whether you have the data, whether you have missing data. So you can actually analyze how well your model will perform. And then you can take action to improve it. And these are already technical solutions that exist that can be applied broadly. In fact, there is a company called CSAIL who will do exactly that for you. They will take your data, they will take your model, and they will assess the uncertainty of your model and tell you where you're missing data, whether the data is biased, etc. So I am actually very positive and optimistic that the technical world will deliver the business vision that Susan laid out for us.
Mm-hmm. Yeah.
Thanks, Heitor Simão. Building on top of this last discussion, we've seen a lot of discussions about using the LLM for real-world applications. LLMs or transformers, they are playback machines. And we haven't seen evolutions on applications that could be used on the real world in a massive way. I'll give you an example. Like, imagine you want to build a salesperson. Okay, salespersons are specialized people on something, mostly. And what we would like to ask you is that, do you foresee the evolution of the coming back to the specialized systems that we had in the past, but not intelligent ones? Like, we're going to have to build specific models for specific transformations or evolutions or real-world constraints instead of being over this GPT fever that we are living today. So this is GPT or those transformers are only playback machines. We need to foresee the future or even build some creativity. Imagine if you want to sell a car, you gotta be a car salesperson, okay? Yeah, if you want to sell a health plan, you gotta know everything about it and how people treat this. How do you foresee this? This is a real problem that we can't address today with those things we we have on hands.
Let me zoom back a little bit from what you said, and I think I'm agreeing with you, but I'm not sure. Yeah, I'm not sure. I think right now the sort of predominant perspective that is being pushed vis-a-vis LLMs is that they are close to plug-and-play solutions for a wide variety of problems that will allow you to substitute away labor, lower cost, do certain things. I think that's roughly it. Kind of plug and play, a little bit of personalization, a little bit of data. And I think, to me, that's very misleading for all the reasons we've described. I don't think that they're plug and play. I think that, sure, for some very specific use cases, they can be. But for most use cases, the plug and play model, I think, is kind of going to ultimately fail. But that doesn't change the fact that they are unbelievably amazing technologies that can do truly astounding things that we could not have dreamt of 10 years ago, which to me means that what actually the high return right now, and maybe this goes back to the first question, is actually a certain kind of creativity and a certain kind of entrepreneurialism in asking, given the real problem, given the real stuff I've got going on, what are places where I can creatively exploit this thing and to meaningfully have impact? And so maybe I'll connect back to the question about training. I actually think to do all of this, it's not about the training data, it's about the evaluation metrics you put forward. It's about properly scoping a problem, deciding what are the metrics you need to know if you've succeeded. That includes bias, but that includes whatever you think is the current form of success, and then being able to work against that. Whereas I think right now we're offloading evaluation to these companies and we're offloading problem specification to these companies. But I think the big return in the next few years will be coming up with appropriate problems that you have metrics for and you can assess, is it working? Is this a way that it's actually succeeding?
Maybe just to pull together two things that both of you said there, like, and with my point about the ecosystem, is that one beautiful thing that they have done is they've made it easy to code and easy to develop, or have like a lot of no-code solutions. This is actually the easiest technology I've ever worked with as a machine learning technology. Just and the tools that are out there are amazing. So my students, like I can take a master's student and they can build something in a week, where like it used to be that like you would build it in a year. So they're just so good. So as long as we have some compute out there that people can get, and we have models that are cheap, and we have an ecosystem of tools, and you can call them developer tools, then the people who are building the machine learning evaluation things, the machine learning technical fixes to the problems, they can do their thing, and we can invent new ways to make it safe. And as people invent new use cases, other people can invent ways to help their use case succeed. And all together, we'll try a lot of different ideas and figure out what works. And so that, I think, to me, that what we want for innovation is to let that evolution happen. And crucially, the scientific community has to be a part of it. We have to have compute, and we have to have models, and we have to, and there's a lot of us in the scientific community that can help try to make this, successful, make it safe. It's like we've got a project of like putting a man on the moon, except for now it's not just a few people locked away at NASA doing the equations, but like we can actually get, a broad swath of society to participate in making sure we can actually land the plane safely. Now, we might blow ourselves up on the way. That is a problem. But I'm not sure that like trying to stick our head in the sand and hold the stuff down is the way to keep us from blowing ourselves up. So we should be very attentive to the fact that there are many ways we could destroy our society along the way.
So I just want to say very quick, hopeful comment about your question related to skills and specialization. With AI tools, you can learn from the best experts in the world how to be more like them. So if you're a surgeon, if you're a resident surgeon, you can learn how the expert surgeon in your domain executes the task, and you can become better. And in any other field, you can basically do the same, provided you have the right data.
Yeah, so I think, just my takeaways from this is that all three of these people who think so deeply about this are fundamentally optimistic. And Susan, you kind of threw me a little bit of a speed bump there with the end of the world comment. I do think it's important to note that they're also cautious. They are also concerned that we think deeply before we act, that we really focus on not just asking good questions, but that we structure those questions in a way that when we get the answer, they are measurable and meaningful in order to make some sort of action. And I do appreciate Susan's comment that there are a lot of scientists that can help along the way. And I think that it's important for the technology community to engage the scientific community, access to compute, collaboration, and so on. And I think that the main takeaway from that is that our society needs to collaborate much more if we're really going to achieve the promise of these technologies and at the same time avoid the peril of the technologies, because no one vertical has all the expertise necessary to direct us in the right direction. So I just want to give a huge thank you to our panelists and to the audience. We are going to break now for lunch, and we're going to have a fireside.